All right, so here's number 3. It says, according to Hubble's law, we're going to use the Hubble constant as, of course, 70 kilometers per second per megaparsec. That's the number that the book it uses consistently. All right, but we're actually going to see a little bit of variation with that. They want to know what the recession velocity is of a galaxy that has a distance of 200 megaparsecs. And then how far away is a galaxy whose recession velocity is 4,000 kilometers per second. So we'll do both of those problems. And then we're going to do the same two problems, the same two numbers, but using H0, the Hubble constant, as 60. The units are always kilometers per second per megaparsec, and then also 80. So it's kind of making like a little table, if you will. All right, so let's get to it. One other thing, let me just point this out as well. There is we've got to look at, and not in this particular problem, but with Hubble's law. When the redshift starts to, when you start to approach about 20% the speed of light or so, once you get into, let's say more than about 20% the speed of light, you really have to use this table, and the redshift will give you what the distance is. Okay, so Hubble's law is a wonderful law that Hubble came up with. But of course, nowadays we can see galaxies that have really, really incredible redshifts, and the redshifts. Notice right here you have a redshift of 1, and there's even greater. Right, it goes all the way up to 8. There's 10, and so forth. What's going on there is remember what the redshift is. It's the velocity. The recession velocity divided by the speed of light. And so if you're above 1, that would be greater than the speed of light. But of course, it can never be greater than the speed of light. We have to use the theory of relativity, all right? And really, instead of using the equations of relativity and having to go through all that, what we're going to do is just use this table. All right, so we really don't need this one for this particular problem. I just thought I'd open that up and take a look at it. All right, so here is our problem. Hold on, let me find this. Let's see, where am I? All right, so problem number 3. These are the 3 Hubble constants that we're going to use. I'll start with the 70 kilometers per second. Per megaparsec, and then we'll do B and C. All right, so A, and basically they give us when the distance is 200 megaparsecs, what's the recession velocity? So it's just 70 times 200. So it's pretty trivial. It's 14,000 kilometers per second, and the megaparsecs cancel, right? And then part 2 of that is, okay, well, what if the recession velocity was 4,000, what would the distance be? And so the distance is just 4,000 divided by 70. So we're going to do the same thing with instead of putting 70 right here, you just put 60 for this one, and then the next part you're going to put 80, and you put the 80 in place of the 70 with both of these. All right, so that's the basic idea. I'm going to do that with you in just. All right, so I just set up like a little table. All right, so anyhow, this first one we just did, this turns out to be 14,000 kilometers per second. That's okay, kilometers per second. All right, so the basic equation is exactly the same, right? It's just taking a different Hubble constant, multiplying it by, if you already know the distance to this object, the recession velocity is just the Hubble constant times the distance. And as long as it's in megaparsecs, remember the units of the Hubble constant are kilometers per second per megaparsec. All right, so megaparsec. All right, so anyhow, like this, that's supposed to be a C. Anyhow, So the first one, it's just 14,000, and then they want to know the distance to, and this is more like you would actually use the Hubble's law. It would just be the recession velocity, which again you measure with the Doppler effect, and well, it's really the red shift, which comes from the Doppler effect, of course, but it's really the red shift that we're interested in. Anyhow, that gives you, the kilometers per second cancel, and that leaves you with 57 megaparsecs. All right, let me do so here are the answers for the other ones. Let's see, so the velocity, when it's, so it would be 60 times 200, so this becomes 12,000, 12, that's supposed to be a 2, 12,000 kilometers per second. Oh, come on, kilometers per second. And then this one, since it's 80, that becomes 16,000. Right, also kilometers per second, right? So it's the same units. All right, and then so using 60 and using 80 as the reason that every textbook does this, because when I first took astronomy many years ago, they actually did not know the Hubble constant to within the accuracy that we know it now. I mean, this number 70 is the accepted value. It's kind of an average value that we've narrowed it down to. But when I first took astronomy, it would range anywhere from 50 to 100. All right, it's just to let you know, that's how amazingly accurate this has become. All right, so anyhow, with 60, the distance, so it's the distance to something that has a recession velocity of 4,000. So it's this exact same thing as this 4,000 divided by 60. So that distance turns out to be 66.7. And the answer is, of course, megaparsecs. Right, megaparsecs. And then this one is 50. It turns out to be 50 megaparsecs. All right, so that's problem number, what one was this? Number 3. All right, they just want you to use the Hubble constant, the Hubble's law in several different ways. Remember, this one does not use relativity. We don't need to use that table, but in the next problems, very soon, we're going to have to use that table. All right, so here's number 5, and as you're going to see, number 6 we have to do this with as well. Use the data table 24.2 to estimate the absolute magnitude and the luminosity of a quasar with a redshift of 5 and an apparent magnitude of 22. So those are the two things we got to remember. The redshift is 5, and the apparent magnitude is 22. All right, so here's the table. So if I scroll down to so it's this first column. This is the redshift. If I scroll down to 5, this number right here, the 8,000, that's 8,000. 8,000 megaparsecs, right? So that's how you get. It would require the equations of relativity to get this, but they've already done these in a nice table. Oops, there it is. So you just scroll down to whatever the redshift is, and then you just look up in this third column right here. All right. And see, this thing is traveling. Just to let you know, right here. Remember, the second column is the recession velocity divided by the speed of light. So this thing's traveling at almost 94.6% the speed of light. So that's we definitely need to use the equations of special relativity. All right, so, well, we don't use them, but we use the table. All right, so let's go back to the problem here. All right, so here we go. All right, I've written everything on, and so I've already looked this up. So we need to figure out what the absolute magnitude is. All right, so what we're going to do is we know the apparent magnitude. They give us that. Little m is 22. And so we want to figure that out, and you know, that's actually not too difficult. We're just going to use this equation that, you know, that we've been using with the distance equation. All right, so the distance is equal to, you know, when you know the absolute magnitude and you know the distance, which we know d is going to, you can solve this. All right, so this is d is equal to the 10 to the absolute magnitude minus, I'm sorry, it's the apparent magnitude minus the absolute magnitude. Remember, that's m sub v plus 5 divided by 5, right? And that's all in the exponent, right? And so then you play the same game. You take the logarithm of both sides. But see, this time we know what the distance is, right? And so this is, by the way, this would be 8 times 10 to the, you know, this is 10 to the third, and then mega would be 10 to the sixth. So 10 to the third and 10 times 10 to the sixth would you just add the exponents. So this would be, you know, another way of writing this distance would be 8 times 10 to the ninth. Right, 8 times 10 to the ninth parsecs. All right, so you know, you're going to take the logarithm of both sides. So remember, this 5 comes over, and so it's going to be 5 times the log base 10 always of really it's 8 times 10 to the ninth. All right, so we got to figure that out, and then that's going to equal 22, remember, because they gave us that, and really what we're looking for is m sub v, and so then it's going to be minus m sub v plus 5, right, plus 5. All right, so you know, now we can actually solve this. Let's see, what do I have? All right, so this becomes, I didn't really write out all my stuff. I just did it in the calculator. Anyhow, you know, you bring the 22. So you know, it's really 27 when you bring it over to the other side, and that's negative. But then you know, notice it has the negative in front of the absolute magnitude. So the absolute magnitude m sub v. This is, you know, this is what we called part A. The absolute magnitude turns out to be negative 22.5, negative 22.5. All right, so you know, very bright object, and so you know, you just solve this. It's not very hard. Take the logarithm of 8 times 10 to the ninth. Just make sure, you know, you make sure you're doing base 10. Right, and then the last part is, oh yeah, we have to figure out the luminosity. So once we know the absolute magnitude, and we already know the apparent magnitude, right? We had that up here. You know, once you know absolute magnitude and apparent magnitude, you can figure out the luminosity. All right. Well, actually, you in terms of the sun, you just need what the absolute magnitude is. All right, so here, let me pause it. And all right, so again, to get the luminosity from if you know the absolute magnitude, it's really simple. It's the luminosity is equal to 10 to the power of, and we're going to get it in terms of the sun, so we have to use the absolute magnitude of the sun. Remember, I mentioned this at the beginning. We have to use this 4.83, and so we're going to minus the absolute magnitude of this. What is this thing? Is it a supernova? It's got to be a supernova. Anyhow, so this is going to equal 10 to the, so it's 4.83 minus a negative 22, so it becomes plus 22.5. 22.5. And remember, that whole thing is divided by 2.5, divided by 2.5. So that doesn't really look like a divided. Anyhow, it becomes 10 to the, what is it? 10 to the 10 to the 10.932. Okay, so when you raise, you know, 10 to that power, here's what I get. I get a luminosity of 8.55 times 10 to the 10th, times 10 to the 10th, times the luminosity of our sun. All right, and the reason it's